So my name is Jari-Pekka Seppänen. I work as NPI manager at Aspocomp Group, and I have been in the business already nearly 2 decades. And today we'll be speaking about high-frequency PCBs, and this is more on the PCB fabricator point of view. Let's share my screen. So, today there are many different areas utilizing high-frequency PCBs. And I think probably the most known ones are wireless communication systems like 5G and satellite comms, avionics radars and antennas, medical systems like MRI, automotive communications, as in driver assistance systems, vehicle communications, consumer side routers, IoT devices, smart wearables even. But also already in industry automation and machinery controlling systems like in the Industry 4.0. So what is then high-frequency PCB? This of course depends who you ask it from. There are even applications utilizing around 100 gigahertz frequency, while for 6 gigahertz might be already an extreme frequency. But generally speaking, I think anything above 1 gigahertz can already be considered as a high-frequency application. And these high-frequency boards usually utilize materials with low dielectric constant and low dissipation factor. Also, complex via matrices and some level of thermal dissipation solutions are often used. Below here, you can see some of them. Most common probably already today is epoxy-filled via farms, solid copper blocks embedded into PCB. This is called coin technology. And even multiple different types of heat sinks where PCBs can be either laminated onto or glued or even soldered. And looking more deep into the materials, I did roughly categorize some of them or some of the well-known materials. We can first look at the C category, where we have our basic FR4 materials. These are the low cost and very easy to produce. B category, this is where it starts to get a little bit fancier, so modified FR4 resin systems, where there's more fillers molded into certain applications. Usually the price increases a little bit, and feasibility-wise, there can be some productional requirements like plasma desmear or specialized drill heat count parameters. So the production is also slightly more expensive. A category, this one includes PPE and hydrocarbons, where dielectric constant starts to settle around 3 to 3.3. Again, same cycle, slightly more expensive and slightly more difficult to produce at the factory. And finally, the S category, which is mainly just PTFE. In this category, there are a lot of materials with very wide range of pricing. Some of them can be slightly more expensive compared to PPE, when some of them can be even tenfold from that. So some of them are extremely specific materials, and lead times can be also very long. Feasibility normally is also impacted. These materials usually require extremely specific thought parametering in the production, and lots of extra steps like baking, chemical preparings, etc. In this table, we have gathered some of the high-speed and high-frequency material. This is actually borrowed slide from our another slide set, but here you can see how a whole lineup of material stretches across TK and TF table. For example, if you take a look at the Rogers 3000 series, which is right here on the bottom left, very small box, and this is due that the lineup has been designed to maintain as close to 3.0 decay as possible. And when we compare it to something like Mectro 6, for example, here, it stretches from roughly, I would say, 3.2 to 3.6, 3.7 decay. And this is due that the lineup utilizes different kind of glass clots or glass weaves, glass weights, and that molds the decay, average decay of the said dielectric around. But this doesn't, of course, mean that you couldn't use something like this in a high frequency application just because that the lineup stretches so far away. They have multiple different material options, even at the low decay side. So there are multiple different options to choose from. So in this graph, I have tried to reflect how different materials are affected by heat, meaning how much material expands or shrinks due to temperature change. Thermal stability is an important factor to protect both from impedance changes when working at high temperatures, but also minimizes stresses coming to via connections and VGA assemblies. It is important to note when utilizing high CTE materials in a complex stackups, predicting the final shrinkage of the stackup becomes always a little bit more challenging when the CTE of the material is higher. And particularly if you mix this material with some other materials, what is the efficiency between the materials, or how do they act with each other? Or if you are doing some fancier blind via stack up where you add continuously material only on one side. Important to remember is that in these cases, the shrinkage curve is not ever linear. So design matters, copper weights matter, different material types matter. This graph is a little bit similar to the one we looked earlier, where we had those little boxes of lineups, but I have added some more high frequency materials here, and the value data points are the average of the whole lineup. Decay and DF are important factors, while dielectric constant is a measure of how well material can store electrical energy in an electrical field. Low decay also has contribution to signal speed, transmission, and frequency. Dissipation factor, on the other hand, is a measure of energy loss within the material, meaning if I put 1 volt in on the other end, how much will come out on the other end. In short, it reduces and prevents signal loss and improves the quality of transmission. Then moisture. Low moisture absorption is an important factor as well, since it prevents material deterioration and also stabilizes the decay and DF. Copper foil. Copper foil's role becomes much more important roughly around 5 GHz and above due to skin effect. And this is due that how rough the copper is, it makes signal length longer. It takes more time for signal to travel from one end to another. But for the skin effect, we have some other slides coming in the front. So where does the copper roughness then come from? There are usually 2 to 3 origins for copper roughness, depending on the whole stack up, how it is built. On the right-hand side, we can see basically whose suppliers' actions are or choices are affecting copper roughness on which side of the copper and in which point of the buildup. So there are mainly foil selection from the laminate supplier who is building the one single dielectric copper flat laminate. Then there are PCB fabrication plant foil selections. So always when they are using, let's say, foil buildup, where your substack or final stack ends up in prepreg plus foil. Then there's of course PCB fabrication plant oxide treatment, which kind of oxide treatment they are using. And currently there are no IPC grading or any of these VLP, HVLP, RTF, RTF2, that what is the range where they need to be if they name their product according to one. So they can basically decide by themselves what is the ranges for each and every one of them. And best is to confirm straight from supplier or even PCB fabrication plant. They can help you as well with these. And the laminate copper foils. So illustration again shows which side of the copper we are speaking of. This is now the side of the copper that is facing the core laminate itself. And normally there are 2 to 3 choices to choose from when ordering material. Usual options are something like RTF, which is a rougher foil, and then VLP or VLP2, HVLP. And these are the finer spec foils. Then the PCB fabrication plant foil options. Unless a certain roughness is specified in the stack-up, PCB fabrication chooses normally which foil to be used. In these cases where the stack ends up in prepreg plus foil. Usually the final copper thickness and PCB via matrix determines pretty far what foil options are going to be used in the PCB fabrication plant. And this is due that there are different possibilities how to produce boards, depending on the equipment that is used at the said factory. So in example, if we would have a board with epoxy plugged holes and plated through holes, one fabrication might choose thicker foil if they would be drilling all of the holes and plating all of the holes in a single go, and then epoxy plugging selectively afterwards. Then they might be choosing thicker foil, which is usually also rougher, in order to hit the final copper weight target. While some other plant, like for example us in Aspocomp, we are drilling and plating epoxy filled holes and plated through holes separately, which requires 2 separate plating, drilling and plating rounds. And for us, it's, for example, more beneficial to use already thinner foil, a little bit smoother foil, so we can save something at the down etching phase where we should then remove copper weight to hit the final target. And this is, for example, set of foils that we are using at Aspocomp. There are, of course, some foils as well outside this table, but these are the most used. Then PCB plant oxide treatment. Everybody has to oxide treat their inner layers and substrate somehow. Without any oxide treatment, the copper surface is not rough enough and lacks bonding agents, and results usually in delamination, where the copper layers are separated from the prepreg epoxy. Aspocomp uses today on-film EX from Atotech, which is one of the advanced oxide treatments in the industry. Here is a table comparing our old one and the current one and their roughnesses. And compared to old oxide chemistry, which only roughened the surface mechanically, or not mechanically, chemically, but roughness, adhesion was mechanical. On-film EX adds chemically separate bonding agents on the surface of the copper to make up what is lost in the adhesion when the mechanical roughness is reduced. Today in high frequency and high speed boards, this is requested fairly often where roughness is not wanted at all. And there we come to skin effect. I slightly touched this subject earlier already. So on high frequencies, this effect is called skin effect, where a signal tends to escape to the surface of the trace as the frequency grows higher. And here we can see that roughly somewhere around 5 gigahertz, we are dialing down to already under 1 micrometer depth on the skin effect, which means here your roughness starts to affect more and more and more of the signal integrity. So I would say roughly 5 gigahertz and above, you should maybe start consider at least simulating with lower profile copper foils as well, at least to see how much the effect would be in the end. There are also different types of fillers in the materials, which allow suppliers to mold materials specifically according to certain aspects like heat resistance, dissipation, moisture absorption, flammability, stiffness, CTE, dimensional stability, warpage, or DK and DF. Then stack-up related challenges PCB fabs are facing today. Quite normal today is multiple plating cycles due to complex via matrix. This means that your blind vias are ending in multiple different inner layer from your top layer or bottom layer. And in this case, you would need to do all these stages separately throughout almost completely whole factory. And like in this example stack up, building PCB gradually only on the other side increases copper weight asymmetrically, which means that the top side gains much more copper compared to the bottom layer, and usually requires many down etchings in between of these rounds, which always increase the tolerance of the copper thickness as well and the copper distribution. Either the way, multiple plating allows variable copper distribution, etching accuracy, lengthened process paths, warp and twist, and also overall feasibility. What would require to be done in order to run this kind of PCB in volume production? Then moving from there, again, keep in mind some complex via matrices, especially on those very small and precise structures on the surface can also lead to yield loss. Continuous plating on the one side, as said, increases the copper thickness and processing of the said layer, which increases all kind of tolerances. And you can't necessarily always say how many times PCB fabricator would be plating this or this or this setup. For example, here we have laser microvia together with bladed through hole. Now, depending again from the equipment, it can be run either in one plating step or 2 plating steps. Then if you add also epoxy filled holes there, maybe 2 or 3 different steps, and then of course all the blind via setups. So in these cases, we do advise to consult the PCB manufacturer to identify any potential issues with the design and maybe even avoid some unnecessary iterations. The illustration on the right-hand side is similar to the board that we already saw in the couple of previous slides, but now only on proportional cross-section view. You can see here that the material thicknesses and copper thickness are extremely asymmetric. And now, depending on the CTE of each material, usually one material tends to shrink more than some other materials. And especially when adding gradually material again only on one side, it makes the top side shrink and shrink and shrink more and more. But this also affects, apart from plating issues, mechanical issues like warpiness. This is actually one test sample from my very own collection. Even though the customer might not see the warping as an issue, especially depending on board size. If the board is fairly small, it maybe cannot be seen as a big issue there. But when PCB fabricator copy paste this basically multiple times, in a bigger motherboard, mother panel, it can start to be really an issue and even a showstopper. So today, many PCB fabricators are utilizing vacuum tables, for example. Work panels do not hold in the vacuum table at all. You need to tape them then in, and still they try to fight their way out from there. Neither you can use any kind of automated loading and unloading systems, which increases, of course, manual labor and handling of the boards, and brings a whole lot of other issues on the table, like scratches and fingerprints. Then in the high-frequency design, traditionally sharp corners are avoided, which leads to an issue not being able to use traditional library elements in the design tool, like, for example, line or rounded pads or square pads or rectangular pads. And these designs are usually often drawn in 3D design tools for simulation purposes. And due to the limitation of file compatibility between the 3D design tool and PCB layouting tool, they are often exported in DXF, which means that the features are drawn in single contour in these cases. Now, if the designer decides to use auto-filling option to try to mitigate this by adding some multiple lines and pads to maintain the rounded shape of the trays, it can also lead into some issues. If thinking big PCB and you would autofill everything, it would very rapidly grow the amount of the data that needs to be then analyzed and used in other CAM stations, like also in the PCB fabricator plant. So the data is much more heavier. Plus then, if PCB fabricator would be using overall or some local edge compensations to try to mitigate any etching inaccuracies, it can also bring some issues where depending on what rules are given to which elements, like contour, which is usually something like ground planes, might then mix up how much different elements get edge compensation in such line. Like here, for example, the bottom side is just a single contour, and then the rounded line here has been drawn with multiple different elements. And this, of course, then results in irregular etching, or also one common issue with such are something called SIP, self-intersecting polygons, which means when your feature has basically minus side width, so it goes past each other, and these can bring a whole lot of different type of printing errors even. But in the end, how fabricators want to see this data is pretty much specific preference between fabricators. Example, us, we can take both in, only that if it's really heavily filled in data, the CAM time might be slightly longer. Then one common feature on the high frequency boards is trace shielding with vias. In these cases, the pitch is a very important factor when stitching ground vias around the tracing. Sudden increase in hole quantity within specific area will utilize considerable amount of plating power, leading to less copper deposition on the surface compared to areas that are outside the dense matrix. The illustration I tried to picture there, how it kind of slides in this area. You don't have any grounding holes, neither on this edge here, and the copper deposition is higher compared to the area where you have your dense matrix, and then the area in between there is something between high and low copper deposition. And when you have features with tight tolerances that are located near both dense and loose matrix areas. They will etch also differently, which means that the fabricator plant in many cases need to run separate test panels in order to see that what is the actual result of etching with this design, and then start to manually add or remove edge compensations in certain areas to try to get as close to nominal outcome as possible. But usually this can take easily time and effort and material wasted just on tests. Then a little bit more about PTFE as a material, very commonly used in high frequency designs, even together with FR4. However, PTFE differs quite much from traditional FR4 production. And as a material, PTFE is also extremely soft, even when reinforced with glass fiber. So mastering drilling, milling, and desmear processes to ensure good whole wall plating is essential, of course. And these can be quite complicated and require some or even much testing when taking new material in use. And it usually requires from process side something called plasma treatment, so we can remove the smear from the drill wall and prepare the whole wall for plating. Even some cases, quite specialized drilling and milling parameters, and even tools, different kind of milling tools and drilling tools. Laser drilling might be an option as well in some cases, but usually it's extremely challenging to get good and stable outcome. PTFE materials tend to outgas as well, so multiple bakings and chemical processes are usually required because of those. And finally, when you mix PTFE together with FR4, now we have extremely soft material that requires a lot of chemical treating, a lot of baking, a lot of everything, more or less. And then we have something that is extremely much more fragile compared to PTFE and much more harder. It becomes even more difficult to carefully look for parameters that fit both of the materials. Then impedance control. For high frequency PCBs, impedance control is important because even minor mismatches can cause significant issues in shorter signal wavelengths. Designers use specialized materials, tight tolerances, carefully thought stack-ups to minimize reflections, parasitics, electromagnetic interference. And advanced simulation and testing are usually always done to ensure that the board meets performance requirements under these conditions. And in this example, I have constructed two calculations which share same dielectric tolerance, same copper thickness tolerance, and same trace width tolerance. So basically only the dielectric thickness changes between these two calculations, and therefore also the nominal trace width changes between these calculations. So when utilizing 5 mm dielectric, the required trace width is narrower compared to 10 mm dielectric. And with the same tolerances, you can easily see that the let's say, like for example, inaccurate etching doesn't hit so hard on wider trace compared to more narrow trace. PCB fabricators can simulate customer stack-ups, including their knowledge over pressed out dielectric thicknesses. The prepreg compresses differently depending on the layout and copper thickness facing the prepreg. So this alters also copper-to-copper distances and has impact to the impedance simulation. Commonly, all PCB fabs are using time domain reflectometers. Measuring is done from separate coupons like this on the lower end of the slide. On-board measuring is extremely rare, I would say, due to the equipment costs and then also difficulties to get access to, let's say, set trays in the actual design. So PCB fabs then construct in these coupons same or basically copy-paste situation from the trays with set trace length, where they use same trace width, same spacing, same trace to ground spacing, dielectric thicknesses, everything. And then these coupons are placed in the actual same panel with the PCB production. And the measurements will be taken from those. And they can be taken from batch to batch or panel to panel, however customer wants them to be done. So to summarize, materials are important. Use low decay DF materials and appropriate copper foils for better signal integrity. Complex stackups and tight tolerances are crucial usually in production. If possible, please relax them. Advanced simulation and TDR measurements help to maintain impedance accurately. And do not over-specify your designs, as they easily become unfeasible. Even if you could get some engineering samples done, volume production could face challenges staying within the same limits. And whenever dealing with very complex PCBs, strongly suggest to consult your manufacturer always. They might identify some issues or suggest some alternative approaches, considering always the series production as well. Finally, I want to thank you all for listening. And next we have some Q&A section, and I will